Chapter 8 addresses the idea of looking at samples and looking at their distribution. And we have to look at samples because we need to use them to predict our population. I can't look at our population, so we have to use these samples to tell me what's going to happen. Is there a pattern? And it turns out that if we look at a distribution of the sample mean, that would be X bar, and repeat the process over and over, we're going to get one of these distributions. Now, one distribution we looked at was skewed right. Second distribution was skewed left. We have this normal distribution, and then we have the uniform distribution. Okay, so if I take all the sample means, so if I had a room of 20, and I take one person versus 2 people versus 3 people, my sample hopefully will better represent my population. So what happens here is that if I go and repeat the process over and over, I continue to take samples of the same size until I have every sample possible from a population, I actually get this distribution. Notice it is a normal distribution, so that allows me to use the table on Chapter 6, page 406, 407. And so that's after a repetitive process, not after taking one, but after taking all possible. So how can you take all possible? Well, you can't. So what happens is we've gotten a predictable pattern. And this pattern, from showing all these X bars in a histogram, gives me a summary of the variability. It shows me how varied I'm going to get. And if I start looking at large samples, they will be a better estimate of the true parameter. Remember, samples are taken to estimate the population. So what we mean by this is that if I was to only look at one person like we did in Chapter 6, I might get someone out here that is maybe 4 foot and someone out here which is 7 feet tall, and there's a lot of variability there. But if I was to take 2 people, if I took the 7 foot and the 4 foot and averaged them together, I would now be at 5'5". So what happens is, as you average, these extremes then get averaged in and don't become as extreme. So what happens is, if we look at your curve, you can see a change in variability. It's less variable. And what if I was to take 6 people and I was to average them together? Once those sample sizes get larger and larger, these outliers affect each one differently and affect each one less than they did in the beginning if I was just looking at single values. They start to offset each other. So that's what we're going to be looking at in Chapter 8, is a sampling distribution of X bar and the pattern that is associated with it. Recall that a parameter comes from a population. That would be mu, and it is fixed, meaning that at that time, if you were to do the same procedure as I on the entire population, we would get the same exact value. Where a statistic comes from a sample, and so the corresponding statistic for mu would be X bar. And what is it for? Well, it is used to estimate mu. And if we're estimating, we want to get as good an estimate as possible. What you also need to remember about a statistic is that it varies. Your sample is going to be slightly different than mine, or maybe very different than mine. But if I was to put them all on a distribution, yours might fall here, mine might fall here. How many of your type of sample are we going to get if it's truly normal? Not very many. The tail isn't very high. So again, we're taking samples to estimate parameters, and what we want to do is get the best estimate that we can. We want to get as close as possible to our parameter, but we've got that idea that it's going to vary. Well, what's pretty neat about this is if you, again, take all these X bars and make a distribution, sample mean distribution, you do get a pattern, and the pattern is the normal distribution. So it allows us to make statements about my population. And because we have this pattern now, we can use a statistic to estimate my population, my parameter. Okay, it allows us to make statements. Now, notice it's an estimate. In other words, X bar is helping me predict mu. We want a good estimate, so you might be thinking, what do you want to do with your sample size to get a better and better estimate? Hopefully it's obvious that to get a better and better estimate, you want a larger sample size. Now what happens sometimes is that we end up, here's mu, we end up with an X bar right at mu, which is a great thing. It is an exact estimate. We will never know if it's an exact estimate unless we absolutely know the population. What sometimes happens is this. We want to estimate mu, but we get an X bar way over here. So if mu is truly at this location, and I get an X bar down here, we say that it's biased. My X bar did not do a very good job of estimating my mu. So again, we say that it is biased. All right, it's way further down than it needs to be. So keeping this in mind that we have this predictable pattern, we're going to look at the average of sample means. Now, what you need to remember is we have lots of averages. In fact, we have three. We have X bar, which is the mean of the sample. We have mu, which is the mean of the population. And then we have mu X bar, which is the mean of all sample means. So it's a really dual mean. It's the mean of the means. And again, we want this to be the best estimate as possible. We want to avoid that bias. Our standard deviation. We have a standard deviation, sigma, which is the standard deviation of the population. And that's if I'm looking at everyone. So again, if we go to those heights, we have someone that's 4 foot tall and we have someone that's 7 foot tall. Okay, there's a lot of spread there. But as soon as I start taking samples, those numbers start to close in on themselves, and guess where they start to close in? They start to come in this direction and this direction, and they're going to go toward the true mu, or mean of the population. So the larger the sample, they all average out, and if I take all of those average and average them again, I get less variability. And in fact, my variability turns into this, the variability of the population divided by the square root of n. So you can see the size of my sample has a direct effect on the variability of my sampling mean distribution. So the bigger the sample size, the less variable. And hopefully it's obvious that you want to have less variability. And I think it's fairly obvious that I'm going to get a better estimate than if looking at one person. Looking at 2 is a better estimate. Looking at 22 is even better. Looking at 2,000, obviously, is even better than that. So how does this all play in? Well, we've already looked at our pattern. We know then it's going to be a normal distribution, and here are our estimators. We have mu being estimated by X bar, but theoretically, if I look at all my X bars and look at their distribution, and take the average of all of X bars, they will center at mu. So it's going to actually be a great estimate. In fact, it is going to actually be the value. And we've got two scenarios that we need to account for. And here they are. We can assume a normal distribution. If my original population is normally distributed, then my sample means are going to be normally distributed. So when I read a problem, and I want to use this curve so I can use that table, I've got to check my population. If my population is normally distributed, then the samples I take from it will also be normally distributed. So I can use that table. I don't have to take many samples. In the real world, we want to take one sample and make a statement about it. The second scenario says, you know what, if my original population is not normally distributed, what am I going to do? Well, it turns out that if the size of your sample is large, if n is greater than or equal to 30, then even though my population wasn't normally distributed, my sample means are going to be normally distributed. My sample means are going to be normally distributed. And if you think about that, it might make some sense. If you start taking averages, those heavy and light ones are going to all work out to the middle. You're still going to have some extreme values, but they're all going to kind of wash out in the end, and you're going to end up with this normal distribution. And that's really important because we want to make decisions about our population. We now have a pattern, so we can now use a table in Chapter 6 to help us make those decisions because of the pattern that these sampling distributions follow. Now, there's a thing called the central limit theorem, and that's just kind of what we described above. As the sample size increases, again, we want larger and larger sample size, the shape of the sampling means, the distribution when I take x bar and plot it in a histogram, that will approach a normal distribution, even if the original population is not normally distributed. So we kind of abbreviate this sometimes called the CLT, and that allows us to use samples to make decisions about population. Mind you, you've got two things to check. Is the population normally distributed? If not, is my sample size large enough? If my sample size is not large enough and the population is not normally distributed, you cannot assume a normal distribution. So in the end here, what's the whole purpose of Chapter 8? It's to help you understand how to compute a z-score again. In Chapter 6, we had a single observation. X is a single observation. In Chapter 8 now, we don't want single observations. We know when we want to look at something, we're not going to look at one item, we're going to look at many. So the average of those many, the mean of the sample, minus mu over sigma, is going to be my z-score. Now, here's the difference. Two of them. I'm looking at x bar in the second one, and I'm also looking at a different standard deviation. The standard deviations are slightly different. Here it was a standard deviation of the population because I was looking at one value. Here it is the standard deviation of my sampling means. The standard deviation, the variance, the variability is less due to looking at samples versus individual values. One more example is if I'm looking at age. In SKC we have a 16-year-old and an 89-year-old. Okay, if I look at individual values, I would have that 16-year-old and that 89-year-old. But if I was starting to sample, those people would be offset by either younger people for the 89-year-old or older people. And so what would happen is then my variability would lessen. So even though I'm following a normal distribution, my steps, my measuring sticks away from mu, who is being estimated by x bar, is less. My variability is less. So I'm going to get a better estimate of mu because I'm looking at more people and not a single value. So when you do your problems in Chapter 8 on that, let's do it, you really want to make sure that you understand the difference between taking one single value and the z-score and how to compute it versus taking a sample mean and looking at its z-score and how to compute that.